Justin Miller, Oxford College Physics. What we're going to look at in this segment is some interference due to thin films. So, have you ever noticed when you look at maybe some soap bubbles outside when you were a kid, that you got these swirling colors emanating from it? Or perhaps you saw some gasoline on the ground or oil for that matter, on the ground, and you get these colors kind of coming from it. Depending on what angle you look at it, you see different colors. Ultimately, that's due to interference from reflected light off of that substance, and that substance having some thin film associated with it. So what we want to look at is interference due to thin films, and just kind of understand the basic concept by which it happens. So if there's a couple things that we want to look at, first off, let's just write this down. Interference in thin films. First off, when we have light reflecting off of a transparent substance, that light, its wave properties, can either produce an inversion or a non-inversion of the wave. Just like when we had waves reflecting off of, mechanical waves reflecting at boundaries themselves. We had an inversion that was possible if the boundary was ultimately fixed, and then we had if the boundary could actually oscillate too, that the wave was preserved in terms of its orientation. There was no phase change. So light behaves sort of the same way, but there's a different correlation with why or how it undergoes the inversion. So, when light reflects off of a transparent substance, the reflected portion may undergo a 180-degree phase shift. So we want to first understand what we mean by portion may undergo, reflected portion may undergo, and what conditions are producing this 180-degree phase change. So in general, we have some substance with N1 and some substance with N2, and anytime we have light interacting at some surface boundary between two substances, where one substance is optically transparent, we will have some reflection and some refraction. So we've looked at refraction before, but we'll always get some amount of reflection too off of the surface. So what we'll have is some light comes in, strikes here, some will undergo some refraction, and some will undergo some reflection. So we've got sort of a reflected path and a refracted path. So here's our incoming. Here's our reflected. And here's our refracted. So this reflected portion right here may undergo a 180-degree phase shift relative to what it's at when it's striking this interface boundary. It may. So, let us look at that. The reflected wave may undergo a 180-degree phase shift. The refracted path does not undergo any change in phase. So whatever it was oscillating at, whatever orientation it is here, it's just preserved and continues oscillating. Some other things going on here, we'll look at that momentarily. Let's just concentrate on this refracted path. Reflected. All right. If N1 is less than N2, there is a 180-degree phase shift. If N1 is greater than N2, there is none. That's it. So when we're going from a lower index of refraction into a higher index of refraction, the portion that's reflected off, this boundary seems like a hard boundary to it, like a fixed boundary, and it produces this 180-degree phase shift. But if N1 is greater than N2, going from a higher index of refraction to a lower index of refraction, the reflected portion sees it as like a soft boundary, and ultimately doesn't undergo any phase shift at all. So that's sort of one thing that we wanted to look at in terms of the reflected ray. So this doesn't really explain anything regarding thin film interference yet. We've got something else going on that's worth looking at. The wavelength of this refracted ray is not the same as the wavelength of this incoming. So the wavelength within the material with N2 is not the same as when in the material with index of refraction N sub 1. Why is that? Well, because there's a change in its speed, right? When it goes from one material into another with different indices of refraction, the index of refraction is ultimately a correlation with how fast light's traveling through that particular substance. If we are going from a lower index to a higher index, light slows down. What does that produce? It produces a bunching up. The frequency is preserved, the speed of light changes, but the frequency has to be well defined. And ultimately that produces or correlates with a change in the wavelength. So going from a lower index into a higher index produces sort of like a compression of the wave itself in terms of its wavelength, and we get that it's spaced together by a finer amount. As if we go from a higher index into a lower index, it speeds up and the wavelength gets larger. Ultimately though, wavelength in the material N2 is lambda sub n, which is going to be equal to lambda times lambda divided by N2. Where lambda is the wavelength, in N1 material. Squeezing stuff in there. The point is that it changes. If N2 is greater than N1, we've got a smaller wavelength, lambda sub n, and if N2 is less than N1, we've got a larger wavelength, lambda sub n. All right, so still, those are just a couple things that happen depending on the indices of refraction and just the case. Still no interference yet, but what we want to look at is a thin film now. So consider a thin film. I'm going to take some thin film. has some thickness T, we'll call it. Thickness of the thin film. And thin, we're talking about like microns thin when we're dealing with visible light. So what can happen is that, let's just take a nice, for instance, like thin film of a bubble, perhaps. We can have that we've got air out here. We've got some material that has some index of refraction, we'll just say N. And then we've got air here. Well, what happens when we look at some incoming light here? Well, if we've got some light coming in, it's going to hit here, it's going to reflect off, right? And it's going to transmit through. So we've got some reflected light, goes off, there'd be a 180-degree phase change because we're going from a lower index into a higher index. That's great. We've also got this going on. We've got some refraction that takes place, and because we're going from a lower index of air into a higher index of the soap, we would have a decrease in the wavelength. So, and then what? Well, we've got within here, we've got a decrease in the wavelength, that's okay, but now it's hitting this other surface boundary between now the soap bubble film and air again. So what's going to happen? Well, we've got that some of this is going to reflect off, and then some of it's going to transmit back through into air. The one that transmits back through into air comes back out into its original wavelength, and the one that reflects off goes like this, and then what? Well, then it is going to refract back out into air. Yeah, some's going to reflect off. I'm not going to worry about that right now. But this one's going to go and refract back out into air. And these two rays would be parallel to one another. And if they're close enough to one another, then they're going to interfere with each other. Ultimately, if they overlap with one another, they're going to interfere with one another. If this film, is really, really thin, and this particular incident ray is very close to normal incidence, or is at normal incidence, these two waves, will overlap and interfere with one another. And then what do we get? Well, we put our eye over here, and we either see constructive interference or destructive interference by some amount. And that's going to dictate really what we see with our eye right there. So you start looking over a soap bubble that's illuminated with white light, and you've got light hitting at a very close normal incidence, reflecting back into your eyes, and you see these different colors. Why do you see the different colors? Because of constructive and destructive interference due to different wavelengths interfering with one another. So we can have strongly reflected red light while we have weakly reflected blue. And what do you see? You see it as more red, or vice versa. So it really just depends on what sort of interference we get. So what we want to understand then is the conditions for the interference for either constructive or destructive, and how they're correlated with all of this. And it really comes down to path lengths. If the path length within this matches up to the same phase when it's exiting with respect to this reflected one, we will get ourselves some constructive interference. Whereas if this path length is off or out of phase by 180 degrees with respect to this one, we'll get destructive interference. But that's really a matter of what's going on here in terms of the reflection at this location, is there a phase change or not, and what's going on here at this reflection, whether there's a phase change or not, and how those two reflected rays ultimately join back up and are either in phase or out of phase. So it all comes down to the thickness and the wavelength of light that's being considered. So let us take a look at that. So let us do this. Let us say that here, note that the index of refraction of air is just about unity. The index of refraction of this material here, we'll say, is greater than that. So we would have a 180-degree phase shift here. Well, here, with air out here, and this being a higher index of refraction, we have no phase shift here. At this reflection, because we have that n is greater than n sub air. So yes, a phase shift, no phase shift. So we need that these two, excuse me, that this path here, this total distance t plus t, has to have some integer or half integer relationship with respect to the wavelength within this material. Odd integer multiples of half wavelengths, so that when it exits, it is in phase with this one. So if it has a half integer wavelength multiple and going down and back up, it will have undergone a 180-degree phase shift overall with respect to when it entered, and exits in phase with this one that's already undergone a 180-degree phase shift. So that's it. So what do we get with this? Well, we get this condition here. So let us throw that up there. So we're going to assume here that we're looking at normal incidence for this incoming ray, or that things film enough to utilize this approximation. If the distance traveled within the film thin film is equal to, approximately equal to 2t, then the conditions are constructive and destructive interference between two waves at the top of the layer are for constructive. If we have the 2t, 2 times that thickness, the total distance that the wave's going to travel within the material is equal to an odd integer multiple of the wavelengths within the material, it will exit and be in the same phase as this other one. So we're going to say this is equal to m plus 1/2 times lambda sub n. Where again, lambda sub n is the wavelength within the material, so we're looking at how many oscillations within the material it has. Why do we want this 1/2 here? Because that top reflected wave already underwent a 180-degree phase shift. So we need effectively that the number of oscillations of the wave within the material is, well, an odd half integer multiple of the wavelength itself. So that when it exits, it's in the same phase as the primary reflected wave itself. So, what can we do with this? Well, we note that lambda sub n is equivalent to lambda divided by n itself. So we can write this as 2t is equal to m plus 1/2 times lambda over n. where lambda is the wavelength of light in air. And m is equal to some integer, 0, 1, 2, 3, dot, dot, dot. With this, we got that 2 nt is equal to m plus 1/2 times lambda. And there is the condition ultimately for constructive interference. So lambda is the wavelength of light that we're considering interference for. M is just some integer, n is the index of refraction of the film, and t is the thickness of the film. So there's certain thicknesses that will give us constructive interference for certain m numbers, certain indices of refraction, which are pretty much set by the material, and certain wavelengths of light. So certain thicknesses give us certain constructive interferences. Certain reflected colors are more are constructively interfering more than others. And we get stronger reflections for certain colors than others based upon certain thicknesses. And that's what you got with these oil sort of layers. It's different thicknesses at different locations, and you get different strong reflections of certain colors. And you see those like, oh, whoa, there's red and there's green, some yellow, a little bit of blue and violet. Depends on the thickness. All right. So we've got constructive. What about destructive? Well, we've got the same correlation here, except for destructive. We have that the two paths have to be out of phase by 180 degrees. One's already got a phase shift, so for destructive, we have that 2 times the thickness has to be equal to integer multiples of the wavelength within the material. So I have m times lambda sub n. Again, if it's an integer multiple of lambda sub n, and one's already undergone a phase shift, they will meet up out of phase by 180 degrees. So what do we get with this? Well, as we had before, lambda sub n is equal to n lambda. We get 2 nt is equal to lambda, m lambda. Again, n is equal to 0, 1, 2, 3, dot, dot, dot. Equal to some integer. So integer multiples of lambda. Destructive interference. So, what you have to be a little bit careful of is really whether this is constructive or destructive and this is constructive or destructive depends on the phase shifts that have taken place. So here's a for instance. So this isn't completely in general. This is for the case where one has undergone a phase shift while the other reflection hasn't. What if they both undergo phase shifts of 180 degrees? Well, if they both undergo phase shifts of 180 degrees, they just have to meet in phase with one another in the same phase that they began in, which means that the path of 2t, this distance here, would just have to be an integer multiple of lambda sub n, which would give us that condition for constructive if there's 2 phase shifts. And it would give us this for destructive if there is 2 phase shifts. Or effectively if there's no phase shifts. So let's just look at this really quick. So consider something like this. We've got a thin film. Let's drop it back. Thin film once again. oil, water, air. And we'll say that we got some N sub oil, N sub water, N sub air. N sub air is less than the index of refraction of the oil, is less than the index of refraction of the water. We'll just say that this is the case here. What's going to happen in this particular case? We got some incident ray coming in, strikes here. What happens? We're striking at a boundary between a lower index and a higher index. So this reflected path here, we do get a phase shift. 180-degree phase shift, because N sub air is less N sub oil. All right, and then what do we have? Well, this continues to go in. There's this little oscillation. Hits this, reflects off, comes back up. Well, here, do we have another phase shift or no phase shift? Well, now we're again going from a lower index to a higher index. This is a hard boundary then. 180-degree phase shift. Because N sub oil is less than N sub water. So we had a phase shift here and a phase shift here. Those two phase shifts ultimately cancel each other out. If the path, if the number of oscillations that this wave within the material has is an integer multiple of, of itself in terms of the thickness, we get that it exits in the same phase as this one. And if they overlap spatially, they interfere constructively. So 180-degree phase shift, 180-degree phase shift. Now for constructive, we have that 2 times the thickness is equal to m times lambda sub n, integer multiple of the number of wavelengths within the material is equal to 2 times the thickness of the material. We'll have that they exit in phase, which gives us 2nt is equal to m times lambda for constructive, and for destructive, we'll have that 2t is equal to odd integer multiple of half wavelengths of the wavelength in the material, which again gives us 2nt times is equal to, m plus 1/2 times lambda. So really these conditions for constructive and destructive bounce back and forth. It depends. It depends on whether the phase shifts cancel each other out. If there's only one phase shift, you start having multiple layers, all sorts of stuff you have to keep track of. Generally we'll keep this with 2 layers. We're assuming normal incidence, so the thickness here is directly related to the number of oscillations instead of some weird angle that complicates things. But that's really it for the thin film interferences. Excuse me. And there we go. Let us look at a little problem. All right, be back. All right, so here's a problem. We've got ourselves an air, oil, glass layer. The oil is going to be the thin film on top of glass, surrounded by air. And we want to know which wavelength of light in the visible portion of the electromagnetic spectrum is most strongly reflected and most weakly reflected. So let us just go ahead and set this up here. We've got ourselves some thin film of oil here. Here's the thickness. This is our oil. This is air. This is glass. And we've got ourselves some incident light ray coming in. We're saying it's at normal incidence. It's going to strike here. Is it going to undergo an inversion, 180-degree phase shift or not? Well, yeah. We've got ourselves that the index of refraction of air is less than the index of refraction of oil. So it's like a hard boundary, so it undergoes a phase shift. Continues going out. And we've also got that this light enters this material here, keeps on going through, and comes on out, comes up, comes out, and will ultimately interfere with this ray because we're looking at normal incidence, kind of draw it like this so we can see what's going on. We ask ourselves, does it undergo an inversion here at this reflection point? And the answer is yes. The index of refraction of oil is 1.21, the index of refraction of glass for this is 1.56. So we've got two inversions here. Here, 180-degree phase shift, and here, 180-degree phase shift. Ultimately, because N sub air is less than N sub oil, and N sub oil is less than N sub glass. There we go. So we've got two 180-degree phase shifts that ultimately cancel each other out. So if we have that 2 times this thickness is equal to an integer multiple of a particular wavelength, it will exit in phase with this, the wavelength that's in that white light, and it will interfere constructively and make that particular wavelength of light stronger. And that's what we want to look at. We're strongly reflected. So let us go ahead and do this. We have constructive interference. It's going to be gotten by 2. N times T is going to be equal to M times lambda. Excuse me. So in this particular case, when we're solving this out for what lambda is, M equals 0 doesn't really give us anything, so we just kind of ignore that. And ultimately, we want to solve this for lambda. The wavelength within air is going to be equal to 2 N sub oil times the thickness of that oil layer divided by M. So we start trying some M values here, right? We could look at M is equal to 1. Well, that gives us some lambda. Let's see. Put this in. 2 times 1.21 times the thickness. We're told that the thickness of this is 0.62 micrometers. So we'll do 0.62 times 10 to the negative 6 meters, and then divide that by, well, 1 in this particular case. And what does that end up giving us? We've got 2 times 1.21 times 0.62, 6. That gives us 2 times 1.21, 62, 10 to the negative 6. There we go. 1.50 times 10 to the negative 6. So that wavelength of light is strongly reflected. The question is that in the visible region of the electromagnetic spectrum? The answer to that is definitely not. This is a pretty big wavelength here. Let's move the decimal place over 3 times, and we've got ourselves 1,500 nanometers. Now that's going to be infrared for sure. So not visible. So what do? Try M is equal to 2. Stick in a 2 instead of a 1 there, and get ourselves 750 times 10 to the negative 7. 750 times 10 to the negative 7 meters, which is about 750 nanometers. That's getting pretty close to the visible region. That's on the far edge of red light. It's still considered infrared, in my opinion. Let's try to find something that's definitely visible in between 700 and 400 nanometers. So, visible, sort of. Sort of maybe depends on, excuse me, depends on the sensitivity of your eyes. Different people have different sensitivities to the ends of the spectrum, but we're just going to go ahead and say, nah, let's try M equals 3. Ooh, that gives me a nice one. We get that lambda is equal to 5.00 times 10 to the negative 7 meters, which is equal to 500 nanometers. That's definitely visible. Check. That is really the edge of blue, transition between blue and green. So this is a kind of bluish green. A little bit more blue than green, but bluish green light. So we get strong interference of bluish green light. So maybe put our eye right there, that's what we kind of see. Well, let's see if there's any others, because sometimes you can have multiple wavelengths that are interfering. Usually, we'll try it. n equals 4. n equals 4. We get ourselves lambda sub 4 is equal to 3.75, 375 nanometers. It's getting into the ultraviolet region. Chances are you don't see that. It's pretty ultraviolet. Anyways, we go with this one right here. Definitely visible, visible region. Here we go. Strong reflection. What about weak reflection? Which wavelengths of light in the visible region are most, or undergo most destructive interference? Well, again, in this case, because we have two 180-degree phase shifts, we have the condition for destructive interference is 2nt is equal to the quantity of m plus 1/2 times a lambda, which gives us that lambda is then equal to 2nt divided by m plus 1/2, which we can write out as 2 times 1.21 times 0.62 times 10 to the negative 6 meters divided by the quantity of m plus 1/2. All right. Let's just do this. So check out some m's here, right? Let's try m is equal to, let's try m is equal to 1. Let's see what happens. So come back in here, get that divided by m is equal to 1. I get about 1,000 nanometers. That's infrared. We're not worried about infrared. Not visible. Move on, try ourselves in m equals 2. Try m equals 2 here. Now I get 600 nanometers. Lambda sub 2 is equal to 600 nanometers. So 600 nanometer light is basically canceled out within those interfering reflected rays there. I shouldn't say rays, waves. There is no 600 nanometer. Right around 600 nanometer, you have weak reflections. So this is kind of reddish orange, yellowish orange. Anyways, that is out of there. What else do we get? Anything else? Let's try m equals 3. Could be others. Ooh, there actually is. Also get lambda 3, about 429 nanometers. Being in the visible region. You don't see them because we got destructive interference for them. So this reddish and this orangish and this violetish don't exist in the colors. Well, we have this bluish green enhanced. So you're going to kind of see this color dominate that white light. There you go. Is there anything else? Probably not. look at n equals 4. And yeah, that starts to, excuse me, drop into the ultraviolet. So these would be the two. We've got ourselves destructive interference 4, and they're weakly reflected. That's basically that. We can look at certain thicknesses that produce certain weak or strong reflections of certain wavelengths. There's all sorts of stuff that we can do with it, but it's all coming down to utilizing destructive or constructive interference, and again, going back to, is there one phase shift, is there two phase shifts, are there no phase shifts? And that's really dictating which correlation is for constructive and destructive respectively. Be careful with that. Other than that, pretty straightforward. All right, thanks, take care.